SwayamPrabha. Digital India. Educated India.
Welcome back. So, let us continue the discussion on our turbulent combustion topics. So, now we have looked at our different combustion models, their theoretical description pertaining to their computational application, and along with their different advantages and disadvantages. So, we started with the gaseous combustion, where we have looked at the simple models, and then we looked at the statistical models also, and then some models which are very specific to the premix case, and then finally non-premix case. And now we move to the discussion on the multi-phase or two-phase system, because so far our discussion which are restricted to the single phase system like in gaseous combustion, and when you move to the two-phase system, this will give you a different kind of approach and different kind of issues. Now, in two-phase system, so that means we are talking about multi-phase. You have obviously it is not only gas, you have some liquid and then gas, but one please note here that even in your two-phase system, the combustion always takes place in the gaseous situation. But when we inject the liquid, what it does, the liquid has to first go into droplet, and the droplet to small sprays, and then finally it evaporates. So, finally the reaction takes place in gaseous phase. So, that means there is a process or there is a time which is required to go through these different stages of the liquid. So, it is not like that unless it is supercritical condition, where actually liquid can just like your solid combustion, where your solid actually react to oxidizer quickly, because due to pyrolysis process solid immediately goes to gaseous state. But in a regular situation, the liquid first needs to be evaporated to gaseous state or needs to move to the gaseous state, then the combustion takes place. Now, before going this is an BP statistical review of 2018, you can see the energy consumption situation across the world, what is the right now, and the database is collected from 1965 to 2017, and the green one, this is where actually you use the crude oil, that means the all this oil burning and all these things from there, that is the level of. Then this is natural gas, this is coal, a small portion is nuclear, there is a small strip of solar, this is hydro, then wind, geothermal, so that is becoming smaller and smaller like that. But interestingly, you can see the energy consumption which has gone up from this level to this, and now even today this is going in an increasing order. That is why we have to keep on thinking how one can actually come up with the different sources to compensate or to fulfill the demand of the energy of the whole world. Now, the thing is that if you use natural resources, they are also getting exhausted. So, we have to come up with some alternative resources, and that is why we got biomass, wind, hydro, these are becoming quite popular, but the conversion rate or the energy production rate is not that high, which can provide really sustainable and meet the demand of that thing. So, this is an 2018 review. Now, what is the situation of the current state of the art of the research in the liquid fuel? So, people may work on the injection So, there where you look at the injection geometry, like how you inject and through which you inject, that means injector geometry, their dimensions. Then people are looking at the breakup, that means when you are injecting the liquid fuel, it has to break up into small droplets or these things, and that is an important phenomena. The reason is that without breaking down into smaller droplet and becoming small spray which will evaporate, reaction won't take place, and rather what would happen, you end up having a large size of droplet and then that can react suddenly. Then obviously the associated phenomena which is of quite interest is the droplet size and their correlation, distribution. So, and then the fuel atomization. These are all coming under the injection. Now, the second part which is another interesting is the spray processes, that means which will talk about spray statistics, where like size, velocity, temperature distribution like this, profiles of the averages and their RMS, spreading angle, breakup, collision, agglomerations, all these are kind of. So, you see the immediate change when you move from single phase, that like gaseous combustion to the two phase liquid combustion, you start getting this kind of things which are not present in your gaseous case. There, I mean itself the gaseous combustion is complicated and there are so many issues, and we still kind of research is going on to come up with the best possible model for different regime and different mode of combustion, but still now as soon as you go to liquid case, it imposes or it brings in different set of problem, and these are the new things like injection related issues, spray process like spray characteristics related issues. This one has to understand and handle it properly. Then if you come down to a single droplet, so you look at the transient effect, ignition, their evaporation, combustion. So in turn you spray actually contains so many small droplets, and that's why we can look at in details the single droplet situation. Now pollutants in sprays, that is another issue which will an obvious problem in the spray calculations, where unburned hydrocarbon, NOx and all these things would form. Now if you look at a single droplet combustion, so this is burning at an oxidizing atmosphere. So here this is the droplet and this is the flame around that droplet. You have the droplet surface, this is R coordinate system, this is RS, that is droplet surface, this is the flame radius. Now here if you plot that, this is RS, this is R and this is the flame, where your fuel is completely consumed and your oxidizer is also completely consumed, and then you can see how the product actually goes up and then come down in the oxidizer side. Now similarly you can see the temperature here, how, and this is ambient now this particular branch between this RS to RF, this is an inner region, that means this is between the flame and the droplet, and this flame interface you can think about the liquid vapor interface, and the RF, or rather the RS one can think about, this is the interface, RF is the flame seat. So that means where completely it is gaseous in state. So there are, now you can see that fuel is evaporated from the, so that means the evaporation takes place from this surface, liquid surface, and fuel vapor reaches to the flame front, and oxygen rather from the surroundings it moves towards the flame front. So that is how the thing actually takes place. This is, you have the liquid there, from liquid this moves this side and the oxidizer moves this side, and that is why you get a flame front on that side. Now, this is a kind of, one can think about around the droplet what kind of or type of flame we can see. Now, here you can see when there is a droplet burns, either you can have a spherical kind of flame shape, this is spherical and this is non-spherical kind of shape. Now, non-spherical flames are generally caused by the convection effect due to the relative motion between droplet and surrounding gas phase. So, that means whatever there is a transfer or heat transfer takes place between that, this happens, but when the droplet is very small and the surrounding gases can entrain easily, the relative velocity between droplet and the gas phase becomes small, and then the diffusion flame surrounding the droplet becomes nearly spherical. So, in this case there is no such change in the relative velocity. So, I mean, though they look simple, one case spherical case and another case is the non-spherical flame, but there is a reason associated with it. So, this case the convection effects due to relative motion between the droplet and the gas surrounding gas phase is different, that is why it happens. Now, here you can see the mechanism controlling the droplet combustion. So, one of the important thing is that here you can see this kind of things happen in your methanol, octane, dodecane, then ATF and all this diesel engine. So, this is all liquid fuels which are actually burned in realistic situation. Now, what happens is that, so this is where the heat transfer effect essentially. Now, then when the from the surrounding the heat is transferred to the these things. So, the point one can think about the parameters that controls the rate at which droplet evaporates and burns. That means, this is the liquid droplet, it has to actually evaporate and burn, and this evaporation will only take place if the heat gets transferred to this droplet from the surroundings, and when that happens it will evaporate like this and then it will go for burning. Now, the rate at which the droplet evaporates and burns is generally considered to be determined by the rate of heat transfer from the flame front to the fuel surface. That means, if outside there is a flame front, then the flame front has a high temperature. So, amount of heat transfer goes towards the fuel or the liquid fuel, that will allow to calculate the evaporation rate and finally the burning. So, one is the heat transfer, then there will be heat plus evaporation, then the heat transfer, evaporation plus then ignition, and finally the reaction. So, the key quantity here is the heat transfer from the surrounding gas to the droplet. Actually, it determines the evaporation rate, fuel and oxidizer mix, and from a stoichiometric isocontour around the droplet, the mixture ignites in the vicinity of it. Now, here you can look at the sort of transient behavior of the droplet, how it varies. One can look at this either book of Kuo or Tans. So, this picture are taken from, adapted from these books only. So, you can see the change of the temperature from one state to another state. Now, this is again an evaporation of a liquid fuel droplet in the quiescent environment. So, that means the outside environment is calm, and then how that happens. So, the idea here is to calculate the evaporation rate. So, this is the liquid droplet, this is the droplet's surface, in the radial direction there would be flame surface, then this is evaporating. So, you can see at the flame surface, this is the infinity, the ambient temperature, and this is the boiling temperature, while at the droplet surface this evaporates and then it go due to reaction all this the temperature increases, which is along the flame front. So, if you come to the single droplet evaporation, then there are some assumption, because already you can see this is quite a bit of complicated phenomena. It is not that easy to handle like our single phase combustion. So, first assumption that is there, it is an isolated spherical evaporating droplet evaporates in a quiescent infinite media. Then the second assumption is that evaporation process is quasi steady. That means at any instant in time the process can be described as if it were in steady state. So, this particular assumption actually eliminates the need to deal with the PD. Now, third, the single component liquid droplet with zero solubility for gases in liquid droplet. So, this allows one to use the phase equilibrium at the droplet surface. So, this is an quite useful assumption, as you can see. Then the important assumption is the droplet temperature, which is uniform, and this is like T droplet temperature is the boiling temperature, where the ambient temperature is quite higher than the boiling temperature. Now, in some of the problems or many problems, the transient heating of the liquid does not greatly affect the droplet lifetime, and more rigorous calculations show that the droplet surface is only slightly less than the liquid boiling point in combustion environment. So, this particular assumption eliminates the need to solve for the energy equation for the liquid phase, and importantly eliminates the need to solve the fuel vapor transport equation in the gas phase. So, that does not require any of this energy equation to be. Now, binary diffusion with unity Lewis number, which allows us to use some sort of an like Swab-Geldovi's energy equation. Then thermochemical properties remain constant, although these properties are greatly vary as we move through the gas phase from the droplet surface to the surroundings. But these constant properties allow a simple closed form solution, but one has to make very judicious choice of these mean values of these quantities in final analysis. So, which will allow you to have an reasonably accurate predictions. Then pressure would be uniform and also constant, no convection around the droplets, and initial diameter of the droplet, that is RS, temperature of the surroundings and oxidizer are known. With all these assumptions, we can find mass evaporation rate, droplet radius history, and by writing the gas phase mass, energy conservation, droplet gas phase interface energy balance, and droplet mass conservation equation. So, if we write those things, then top of that the gas phase energy equation gives us the temperature distribution within the gas phase, which in turn allow us to evaluate the conduction heat transfer to the droplet at the into the droplet at that surface. So, this is very much very necessary to evaluate the surface energy balance that yields the evaporation rate. So, once evaporation rate is known, we can easily find the droplet size as a function of time. Now, we write down the mass conservation equation. So, this is d, this is we are writing in r coordinate system. So, d rho u r dr 0, which means rho u r square is constant. Now, mass flow rate, if it is independent of radius, then mass flow rate of the fuel and the droplet side would be constant. Now, this is a energy conservation equation, which is a Swab-Geldovi's kind of form. We can write 1 by r square ddr of r square rho u r Cp dt plus rho d Cp dt dr, and change in the enthalpy, the action term. So, that is how you write the energy equation. Now, the governing equation becomes, then this is the set of governing equations, ddr of r square dt by dr equals to m dot cpg 4 pi k dt by dr. This is, so one can write ddr of r square dt by dr equals to z m dot dt by dr, where z is defined like this. So, that is a parameter or term which you can define and rewrite the temperature equation. And then to get the solution for this, you need two boundary condition. When r is at Rs, it would be the boiling temperature. When r goes to infinity, it should be the infinity temperature. So, using these two boundary condition, you can find out the solution. So, the first integration will get us r dt by dr equals to z m dot t c1, and the second integration gives us the 1 by z m dot ln z m dot c1 the c2. So, from the previous equation we get this, then from here we get this. Now, the first boundary condition if we apply, when t r tends to infinity, it would be t infinity. So, if we put this, C2 becomes, so you can use this one here and get C2. And once we put the second boundary condition at the droplet surface, it will be boiling, that C1 becomes like this. Now, you substitute the C1, we get C2 equals to, so here you put the from C2 using the value of C1, we get 1 by z m dot ln z m dot t infinity minus t boiling 1 by exponential of that. So, the final solution will look like this. So, which will look like t infinity minus t boiling, that is an expression which you can, and this is an simple, we started with an temperature equation and through integration you can obtain that. Now, that is the final solution. Now, we go to the next level of balance, where at the droplet interface is the energy balance at the droplet surface. So, from flame the heat will come out, and then the droplet surface will evaporate or the liquid will evaporate, and this is the liquid which is going in. That means m dot h liquid which is coming in, that will be the energy, this is coming in. So, the conduction energy would be m dot h vaporization minus h liquid. Okay. So, at this surface the energy balance will get us that, which is m dot h f g. Now, the rate at which happens, so if we write 4 pi r s square gamma g a lambda g dt by dr at r s equals to m dot h f g. So, differentiating the equation of the gas phase temperature T r at r s, we get dt by dr at r s equals to this. Now, this is what we get from the dt by dr at r s, that is our gas phase calculation. So, we are differentiating that gas phase equation at r equals to r s and we get this. So, now we can find out the evaporation rate, which will be m dot equals to 4 pi r s lambda g by C p g ln B q, and B q would be is known as the Spalding number. So, this expression for the Spalding number is derived based on the heat transfer consideration alone. Other definition of Spalding number is possible, and their functional form will depend on the assumption that is made. Then also one can clearly see that evaporation rate is dependent on the heat transfer through the Spalding number. This is what it is, and it depends on the gas phase properties such as conductivity, specific heat, for which we need to use suitable average values between droplet surface and ambient. Now, different fuel, it has different boiling temperature, different latent heat HFG, and Spalding number and evaporation rate will change with multiple fuel, which is quite obvious because these thermophysical properties are there which are used in this particular equation, and different fuel has the different. Now, also BQ, this factor has a different definition if a spherically symmetric flame is assumed to surround the droplet. So, this will be discussed later on when we will be talking about the burning droplet. So, now if you look at this completes the analysis of the gas phase. Knowing the evaporation rate will allow us right to mass balance, which can be used to calculate the droplet diameter. Now, we write the liquid mass balance equation. So, dmd by dt would be minus m dot, which is this. Then if you rewrite the terms in droplet diameter, it will be d2 by t in like this, and once we integrate we get this. So, this is a Fermat d2 law of evaporating droplet, and the slope would be minus k, which is like this. So, this is now in the liquid phase. So, once we had the gas phase and moving to the liquid phase, this is what we get. Now, we can look at the mass transfer based analysis of droplet evaporation. This is the droplet and Rs is the droplet size, this is the environment, and so the mass conservation m dot r would be constant, m dot double prime would be m dot f, and oxidizer would be 0. So, the species equation m dot f would be yf m dot double minus rho d this. So, along the radial directions how the fuel is changing. So, once we rearrange that, this m dot would be 4 pi r square like this. So, after rearranging we can write. Now, it requires two boundary condition. So, at Rs this would be yfs, and that means the fuel at the surface, and yfr would looks like this. So, this is an expression that you get how the fuel is going to vary from the liquid surface to the other side. Now, we have yfr, this is the distribution of the fuel. So, this is our fuel distribution, and finally we use r tends to infinity, it will be yf infinity. So, the evaporation rate will become m dot equals to 4 pi by, why by is given like that. Now, if you use the Clausius-Clapeyron relation where Pfs is like this, then the fuel yfs can be written where xfs like this. So, based on heat transfer, we write m dot equals to 4 pi lambda g Rs by this, where Bq is this one. So, that requires the effect of your Spalding numbers and these things. Now, we can continue the mass transfer based analysis. So, basically we can look at that when you look at this heat transfer based analysis, this is what you get for the evaporation rate, and this is one can question that what happens when the unit Lewis number is unity. So, we will stop here, and the mass transfer based analysis will continue in the next lecture. Thank you.